Previously, you've learned about different forms of energy, such as energy kinetic, potential gravitational energy, chemical energy, etc. But did you know that different forms of energy can exist in the same system and transfer from one form to another? In today's lesson, we're just going to focus on energy, gravitational potential, and kinetic energy. Consider a bike at the top of the hill when it isn't moving. All energy in that bike is energy from the gravitational potential. As the bike starts moving, the energy is composed of energy gravitational as well as energy kinetic. And at the bottom of the hill, all the energy is energy kinetic. This can be known as conservation of energy and is determined by the law of conservation of energy. Energy cannot be created or destroyed in an isolated system. An isolated or closed system is a system that doesn't interact with external systems, which means no new thing can come in or out of the system. In real life, all systems will interact with other systems, which means that energy will be lost by friction, as heat, as sound. But with the law of conservation of energy, we're pretending that all that energy is staying within the system. Consider a roller coaster. Essentially, the same thing is happening as with the bike, but with a roller coaster, there could be lots of different heights. The important thing to keep in mind is just that whenever there's a height, there's going to be gravitational potential energy, and whenever there's movement, there's going to be kinetic energy. Let's say that the roller coaster is partway up the slope or partway down the slope. Because there's that height and as well as that movement, there's going to be both kinetic and potential energy.
Now let's see some practice questions. When doing practice questions, always remember to find the energy initial, and it will equal to the energy final. So a 50 kilograms snowboarder starts at the top of the hill. That's 20 meters high, and then it has an initial speed of 10 meters per second. For A, it's asking us to calculate the mechanical energy at the top of the hill. And of course, mechanical energy is composed of gravitational energy plus kinetic energy. The equation for gravitational energy is mgh, and the equation for kinetic is 1/2 of mv squared. So our mechanical energy will be 50 kilograms times g times 20 meters, that's the height, plus 1/2 times 50 kilograms times 10 meters per second squared. Let's assume that g is 10. Our final answer will be 10,000 plus 2,500. That will be 12,500 joules. For the second question, it's asking us to find the speed at the midway point and the bottom of the hill. Let's take a look at the midway point first. So when it's at the midway point, the height is 10 meters. And then we set up the equation, Eg plus Ek, these are the initial, equals to Eg plus Ek final. And of course, we already got our Eg plus Ek initial in question A. That's going to be 12,500. We just directly write it down in the left side. And then let's take a look at Eg plus Ek final. So Eg is mgh, now the h is 10 meters, plus Ek final, 1/2 of mv squared. The v is something we don't know, so we'll see. Now we know that the h is 10. We assume that g is 10 again. We are able to have our equation set up. 50 times 10 times 10 plus 1/2 of 50 times v squared. Now we can solve for v. V will be 10 times square root of 3 meters per second. Now let's see the speed at the bottom of the hill. Since gravitational energy only exists when there's a height, when the snowboarder is at the bottom of the hill, there's no height at all. Therefore, the snowboarder will not have any gravitational energy. Therefore, all the energy that the snowboarder has right now is kinetic energy. So we write down our energy total. That's always going to be 12,500 because we assume that it is a closed system. There's no energy loss. Therefore, the total energy will always be this. And then since it only has kinetic energy, we're just going to write down 1/2 of mv squared. And of course, m is 50. We are able to solve for v. V will be 10 times. Now let's take a look at the extension of conservation of energy. Let's take a look at this question. A 20 kilometers brick falls from a rough hill, and then the initial speed is 10 meters per second. Initial height is 10 meters, and then after it reaches the ground, the speed becomes 15. So it's asking you to calculate the energy loss due to friction, because you may notice that this is a rough hill. So you'll have energy loss as heat due to friction. So we are required to calculate for the energy loss. Okay, now let's see the energy initial. Energy initial equals to all the mechanical energy, which is gravitational plus kinetic. That will be 20 times 10 times 10 plus 1/2 times 20 times 10 squared. And you may notice the benefit when doing this is you don't need to care about the angle because we have the speed squared. So the angle doesn't actually matter because we are using the net speed. So the answer is 3000 joules. Now let's take a look at the energy final. Of course, when it reaches the ground, there will no longer have gravitational energy left. All the energy will be kinetic. That will be 1/2 times 20 times 15 squared. This will equal to 2250 joules. As you can see, the energy initial does not equal to energy final because, like I mentioned, this is a rough hill, and since there is friction, a part of energy will be lost due to friction. And it's easy for us to calculate that part of energy. We just use the initial energy to subtract the final energy. That will give us 750, and the 750 joules is the energy loss due to friction. Remember, for this question, it is also a closed system because except for friction, there's no other forces like wind or something, etc. Therefore, all the energy loss will be caused by friction.